Bonjour.
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 Tu nous entends, oui?
Oui,
Ok, parfait, ça marche. Tu vois?
je vous vois pas, mais
Tu vois les slides?
start with my phone installing an app. So I'm connected.
Thanks.
Hello. So, hello Ali. So, hello everybody. My name is Andrea Cherubini. I'm professor des universités at Centrale Nantes and researcher at LS2N in Nantes. And today I'm very happy to head the committee for the PhD defense of Ali Srour, who is defending his PhD thesis on the entitled Planification robuste pour systèmes robotiques. So this PhD is would eventually be delivered by the École doctorale of Université de Rennes, and I was myself reviewer for the PhD of Ali with my colleague Fabio Morbidi, maître de conférence at Université de Picardie Jules Verne Amiens. So Ali carried out his research under the supervision of Paolo Robuffo Giordano, directeur de recherche CNRS at IRISA Rennes, and with co-supervisors Antonio Franchi, full professor at University of Twente in the Netherlands, and Marco Cognetti, chair de professeur junior at LAS Toulouse. We have also remotely connected the examiner Isabelle Fantoni, who is also a colleague of mine at LS2N Nantes, directrice de recherche CNRS. So now Ali will present your work in 45 minutes approximately, and then we will have a question session and deliberation by the panel afterwards. So
Thank you.
The floor is yours.
Thank you. Hello and welcome everybody. My name is Ali Srour, and today I will be presenting my thesis, Robust Planning in for Robotic Systems, under the supervision of Paolo Robuffo Giordano, Antonio Franchi, and Marco Cognetti. So first I will be starting with a general introduction and motivation behind our work, and then I will be delving into a literature review about robust control. And then I will be speaking about trajectory optimization through sensitivity analysis, which is the main core of our thesis. And after that, I will be speaking about the contributions. We have in total 3 contributions. And then I will be concluding with some future remarks. So major challenges in robotics is actually to enhance system autonomy, where the robot has to operate by its own, and ensure that the system is safe among people and other robots. And also enhance the flexibility and adaptability of this robot while dealing with the new scenarios. However, the systems actually operate under real conditions, while their decisions are actually model-based. And these models are actually an approximation of the reality. They are uncertain. Model uncertainty can be modeled as a generic process actuation noise if no information is given about the system. However, if good models exist, uncertainty can be given a certain structure, like a parametric uncertainty. Take an example, a quadrotor UAV that has an uncertain thrust coefficient that is very difficult to measure it differs at each runtime. And also, this quadrotor UAV needs to track a desired trajectory to deliver a package. This package can have some unknown dynamic properties like mass. And also a robotic manipulator inside a factory can have some joint friction, which is unknown, or maybe is tasked to manipulate a payload with unknown dynamic properties. So the issue in robotics actually, while robotic tasks become more and more complex, performance and safety can be limited by this parametric uncertainty. A cool example about parametric uncertainty, did you know that a slice of cheese actually almost caused a crash? This happened with the GSP company. It's in Switzerland in 2024, just recently. They attached a slice of cheese to the base of the rocket while in the descent. And this rocket actually lost roll control and which caused engine saturation. So a small undesirable aerodynamic effect can be a cause of a crash. The rocket ended missing its landing pad by about 40 centimeters. So in robotics and aerospace, even minor factors can have amplified effects due to the system dynamics. So in the literature, how to cope with uncertainty? You usually neglect uncertainty, consider it small enough, but this would necessitate to have accurate models. Add integral terms or adaptation rules, but this would slow the system responses and would degrade the transient state. Or robust controllers to reject disturbance or noise, but this would be a trade-off for performance of the system because robust controllers are usually designed for the worst case scenarios, but it's not the best controller to be chosen if your system is operating at the nominal parameters. So our solution is robust control-aware motion planning. It's about picking your favorite controller and then optimizing the reference trajectory such that the task execution is most insensitive to these parametric uncertainties. And this is actually a generalized method for any choice of system controller. The advantages that you get is that the smartness is actually shifted on a proper trajectory planning rather than designing sophisticated control laws, and that the stability becomes less of an issue because you are able to choose the controller that you are comfortable with or statistically proven for your system. Take an example, these two birds, they both have the same structure, they both can fly very well, but one had a robust methodology in reaching the biscuit and the other didn't. So these examples can be found really in nature everywhere. So about now, we will delve into a small literature review about robustness. So when we speak about robustness, the primary goal is to meet some system requirements. Example like stability, safety, precision, performance of the system, when the system is perturbed from its nominal behavior. Two main philosophies in the literature to tackle this problem, it's always that either you go for robust control methods that improve robustness by controller design, or you select a robust trajectory where robustness is achieved by proper trajectory planning. And because the majority of our thesis will speak just about robust trajectory, I will be in this literature review speaking about just robust control methods. So integral action is one of the most common used methods for rejecting system disturbances. It serves actually as a compensator for modeling errors in uncertain systems, and also provides robustness against external disturbances and parametric uncertainties. So, but it comes with a limitation that it can have poor response to disturbance with rapid dynamics, and also it can cause instability if not tuned correctly, which would lead to actuator saturation, backlash, and rate constraints. To mitigate this effect, anti-wind up techniques exist in the literature, consist of halting the integration process, offloading the integrator, but this technique is somehow conservative before reaching the, you have to set this technique in a conservative approach before reaching the actuation limit because the actuators are subject to uncertainties. Another common method is incremental nonlinear dynamic inversion, NDI. It's a sensor-based technique designed to handle severe disturbances. First used for quadrotor UAV under wind gust loads, and which made it gain its reputation, especially after the improvement that it got from 0.5 meter tracking deviation with the classical PID to only 5 centimeter deviation with NDI at wind speeds reaching up to 4 meters per second. Just an intuition about the control loop, it's designed, the control command depends on the previous control command, plus an inversion of a control effectiveness matrix and servoing on the acceleration level. The limitations are actually quite obvious. It's highly dependent on accurate sensors and also needs effective filtering methods because you are serving on the acceleration level and especially for the angular acceleration, which is not readily available, and you have to differentiate to get this, and a lot of filtering is included. And also it requires precise knowledge of the wind model and the UAV structure, which all prone to parametric uncertainties. Another cool approach is introduced by Phyllis in 2009. It's a model-free controller. It addresses the challenges posed by uncertain systems, MFC depends on this ultra-local model that is updated frequently to estimate the external disturbance that affects the system or the internal ones. And basically, it depends on the knowledge of the input-output behavior. It's not explicitly defined. The advantage is that it's easy to tune, augmented with any feedback controller, as MFC is not a standalone controller by its own, and it's model-free. At ENAC, they used these kind of controllers as to transition between flights, because it's very difficult to have models of answer, because a lot of parameters are included in the uncertainty in the transition. So it's very difficult to explicitly model these aerodynamic effects, and it proved good accuracies. The limitation is that the ultra-local model actually requires update at fast rates and needs filtering for the noisy system output. Model predictive control has shown actually promising results for quadrotor control, but because model predictive control make its decisions based on the model of the system, it can have degraded performance if high fidelity models are not considered. The solution, as in the paper referenced above, that you augment MPC with some adaptive controller to learn uncertainties online. And the advantage of using model predictive control is that you always have this optimal solution, and it works well with handling system constants. However, the limitation is that it's highly dependent on the model of the system and disturbance, and it demands significant computational demands and memory resources, which make it really difficult to apply for standard runs. So now for the main theoretical part of our thesis, trajectory optimization through sensitivity analysis. We start with the problem definition. Consider the system defined by ordinary differential equations, x dot, a function of the states of the system, the input, and possibly uncertain model parameters p. The control goal is actually to track a desired trajectory as d, which is a function of control points and time. And then you pick your favorite controller that is able to solve this tracking task. This controller would be a function of the states, the parameters around the parameters at the nominal value, and it can have internal states, c dot, which can be of integral action. So here we have to differentiate between two cases, actually. If P is equal to PC, meaning that the parameters inside the model do not deviate much from the nominal, so they are equal to the nominal parameters, the control task can be realized very well. However, if this is not the case, you have parametric uncertainty and possibly degraded tracking. A possible metric to capture the idea of the sensitivity with respect to the parameter variations are both the state sensitivity matrix and the input sensitivity matrix, which show how variations in the of the parameters around a nominal value would affect both the state and the input respectively. Matrix pi, however, does not admit a closed loop form expression. The dynamics can be made explicit as follows, and we actually calculate pi dot, we integrate it to get pi. With the controller state sensitivity being how variations of the internal states of how variations in the parameters can affect the internal states of the controller. And now matrices pi and theta can be used in the context of trajectory optimization. The reference trajectory can be optimized with the following objectives, as done previously in the lab. Minimization of the state sensitivity at the final time to reach its desired location, while changing, of course, the decision variables would be the shape of the trajectory. Minimize the state sensitivity over the whole trajectory so that you increase the tracking. Or minimize the state sensitivity at a certain time while minimizing the input sensitivity along the trajectory so that you have the inputs not varying that much from the nominal case. However, there is a more intelligent way to address this problem, and it is with the tubes. So we can actually compute the tubes representing the envelope of the perturbed evolution of the states and input, and we can actually deduce a new norm to be placed inside of the old norms, which depends, by the way, on the Frobenius norm. So we assume for the calculation of the tubes, we assume that each parameter can vary in a given range delta pi around the nominal case, And then we define this range matrix diagonal. And one can project one can deduce the ellipsoid in the parameter space, with delta p being how much is the deviation with respect to the nominal parameters. And then with leveraging the first order approximation of the sensitivity, delta x is equal to pi delta p, one can deduce the ellipsoid in the state space. And with the same reasoning, one can also deduce the ellipsoid in the input space. And now these kernel matrices k pi and k theta would capture how delta pi actually affects the deviations in states and inputs. However, if you are interested in in finding the maximum deviation along each component of the states, and also the input is analogous problem, you can find this scalar, let's say, or radius of the tube for any direction in the state space. And this would allow you to calculate actually the perturbed tubes, which is a set of ellipsoids, along each component centered around the nominal value, along each component of the states centered around the nominal value. And the radius can be deduced from the reference above by such, depending on the kernel matrix. And also the input is analogous and would depend on the kernel matrix of the input. So for the novel optimization problem, each optimization problem would consist of the decision variables, the objective function, and the constraints. So for the objective that we take a new sensitivity norm, which is weighted by W. We call it weight by W, which is the maximum eigenvalue that I can suffer along the states, which is the maximum eigenvalue of the kernel matrix K pi. And the decision variables in our case is the parameters that shape the trajectory. Take an example, we want to obtain the red trajectory such that we have as an objective a minimized, let's say, uncertainty ellipsoid while navigating through a window. The constraints, we take the usual constraints on the boundary conditions of the control points, and also we take the perturbed inputs as bounds. Here we don't actually limit the nominal case of the input as not to hit the limits, but we limit the maximum deviation that the input can suffer. So that's why we call it robust constraints, and we will be speaking about it later on in the contribution section. So now for the contributions, the first contribution was at IROS 2023, where we went on exploring this kind of joint optimization problem for both the trajectory shape and the control gains. And also we wanted to study the impact of the controller choice and gain tuning on the state and input sensitivity. At IQUAS 2024, we validated this approach on a standard drone equipped with a commonly used controller. And our interest in that project was actually to enhance the quadrotor state and inputs robustness in applications of traversing a window. And finally, because all the sensitivity has been worked on drones so far, we extended this to include another robot, which is the Manipulator, and we applied this theory in the scenario of package handling inside the factory. And we showed with a comprehensive statistical campaign a major accuracy improvements for our method. So we start with the first contribution. The motivation was that previous works actually relied on a single control strategy, the dynamic feedback linearization. There was no exploration about different controllers. And we wanted to explore this joint optimization that can optimize both the controller gains and the reference trajectory. So for this, we suppose that states, the normal states, you have the position, the velocity, the orientation, and the angular velocity, be the states of the system. We define the quadrotor model as in the reference above in Antonelli, and the allocation map, which maps the forces and the torques of the controller to individual motor speeds. And motor speeds can be deduced by the inversion of this matrix. And the difficult to measure parameters in this contribution, we suppose it's Kf, K tau, which are the coefficients of the thrust and torque of the propellers, and Gx and Gy, which are the shift in the center of mass of the drone. So in this contribution, we actually consider three controllers. The near hovering controller, which is the most used control strategy everywhere. It's based on the linearized PID controllers. The geometric controller, which is a popular control strategy to deal with maneuvers. And the sliding mode controller, which is a robust controller that deals well with model uncertainties. And we consider actually for each of the controller three optimization problems. The first optimization is optimizing the shape of the trajectory. The second one, OPTK, optimizing only the gains. The third one is optimizing both the shape and the gains. And this is done for minimizing the maximum deviation that you can suffer on the states at the final time. And the init trajectories that we use are trajectories with the optimization objective of the minimum snap along the trajectory as to have a smoother trajectory as an initial guess that respects the actuation limits. And we are interested in improving the accuracy of the position at the final time. The total number of trajectories we've taken for the statistical campaign is 25 for each trajectory case. So basically it's 4 entourage, so it's 100 for each controller with respect to all the cases. And for each of these trajectories, we do 30 simulation in the perturbed runs. Other parameters lie inside the ellipsoid with 15% deviation on Kf and K-tau and 15% deviation of the total arm length L for Gx and Gy. Here we display only one trajectory for all the cases and the controllers. The cases are on the rows and the controllers are on each column. And here we have the 30 perturbed simulations, and we report the final positions of each of these simulations. And you can somehow deduce the uncertainty ellipsoid at the final time. And it's clear that across all the cases, on all the rows, it's clear that the optimized, the joint optimization had the best performance where it's the minimal, so the size of the uncertainty ellipsoid. And we also wanted to actually explore how much each of these parameters are affecting the deviations of the states, X, Y, and Z. So we deduced actually that Kf was affecting mostly Z, the state Z with the deviations, and Gx and Gy were affecting both X and Y. However, K-tau had negligible effect compared to other parameters. And now we display the full statistical study based on 25 trajectories for each of the cases with the simulation 30 times in the perturbed cases, in the perturbed runs. And it's clear that the joint optimization in red was the best. First, we actually tuned all the controllers such that in the init case, they have a comparable median. So it's about 8 centimeters. And then we actually went through applying these 3 optimization problems. It's worth noting that in the joint optimization, we had the best performance where it decreased from 8 centimeters to 2 centimeters only as a median, irrespective of the controller choice. For the sliding mode controller, for example, in orange, you have the optimization of the shape didn't change much the median. However, the optimization of the gains changed it twice. So it decreased 50%. So basically, we can conclude that changing the shape is not a relevant factor for the sliding mode controller, but changing the gains is more of a relevant factor. And for the near hovering and the Lee controller, both were affected by both optimizations, the shape and the gains. So both of these are relevant factors for these controllers. So in summary, the joint optimization is effective in mitigating the effects of parameter variations. And we actually managed to study the most influential parameters that affect the states. However, the main limitation is that lack of experimental data so far. We didn't experiment with a real quadrotor UAV. And the importance of the input sensitivity inside the constraint was not studied in this contribution. And also, the bottleneck of this contribution is the computational times, where you have 2 to 4 minutes per trajectory, not in real time. However, it's worth noting that before starting this PhD, the computational time were about 25 to 30 minutes, so it decreased significantly. But the main priority of this PhD was not computational times, it was more about the theory and the implementation and the validation. So for the second trajectory, for the second contribution, our motivation was previous works actually in the sensitivity framework focused solely on simulations of the UAVs and never made it to the experiments. So we wanted to show that this method can be used with a standard drone that you have in the lab with a standard controller commonly used. And we wanted to show the importance of robustifying the inputs by the tubes. In this contribution, we consider a different model for the quadrotor, which takes into consideration the shift in the center of mass. We define, of course, we have the forces and the torques acting on the quadrotor, and then we define this inertia matrix. The inversion of this inertia matrix multiplied by the force and the torques would give you the linear and angular velocities in the body frame. And then you can write actually the quadrotor model of the displaced center of mass. And we used in this contribution the PX4 controller, which is widely adopted in the community. We did a reverse engineering so that to add it to our sensitivity framework from the GitHub pages. And it has this kind of cascaded structure, consists of PID controllers, and it consists of 4 stages. Here, the allocation map is different because we don't consider the shift in the center of mass anymore in the allocation map. We consider it in the model. The uncertain parameters we consider in this contribution was Kf, the shift in the center of mass, and the mass. And the aim was to actually optimize the shape of the trajectory as to minimize the maximum deviation that we can suffer on the states at a specific time of interest, TW. In the older contribution, we had at the final time, but now we are interested in another point, which is at TW. And we applied, in this contribution, we applied the methods on 2 distinct trajectories, with trajectory 1 of 7 seconds and trajectory 2 of 5 seconds, with the cases, each one has a case init and OPTA. The initial trajectories are obtained actually by the snap pre-optimization, as before, and the drone have to pass through the window with about 2 to 2.5 meters per second. The main goal is actually to evaluate the precision of traversing the center of the window at RD-TW. The perturbations were done by altering the URDF description of the iris model, following the uncertainty ellipsoid in the parameter space. In the real experiment, it was done in a different way, the same way, but it was done by actually extending the drone by a shaft and then placing some tools on the drone so that to modify these parameters. And in total, we have a nominal case, 1 in nominal case, and 11 perturbed cases, both in simulation and experiment. So here we display on the first row, you have the trajectory 1, and the second one, and the second row, you have trajectory 2, with in each column, you have the init and you have the optimized. In total, we had the distance to the desired target in trajectory 1 for the init case was about 14 centimeters. It decreased to about 9 centimeters in gazebo in simulations, with much less variations with the sparsity of the solution. And for trajectory 2, we actually had 0.3, it's 30 centimeter distance to the desired target, and it decreased to about 12 centimeter with much less variance. For the experiment, it was a different case. The actual distance to the desired target decreased from 9 centimeter to 7 centimeter in the optimized case. And for trajectory 2, it decreased from 19 centimeter to 16 centimeter with much less variance. because of the lack of time, we just display the videos of trajectory 2, which is more challenging than trajectory 1 because of the high acceleration at the start, relatively high acceleration at the start. On the top, you have the videos. On the bottom, you have the visualization in PyBullet of the actual data logs. And we introduced in the visualization the actual window. So after all of this experiment, you can have a comparison between the uncertainty ellipsoid on the state, and it's obvious the minimization. So the uncertainty ellipsoid is actually minimized, and it had a lower risk of collision. So in the init case, we had about 50% collision, and it decreased to about 25%. So we spoke about the input sensitivity, but we didn't see it in real. So now we will speak about how we can robustify any function of interest. So we recall that the input sensitivity is how the variations of the parameters are affecting the input, and then we were able to actually project from the first order approximation the uncertainty ellipsoid of the input space, and then we were able actually to find the maximum deviation along each of the components of the inputs, and we included these tubes inside the constraints of the optimization problem. So for this, we display the actuator speeds U3 for trajectory 2 in the experiments, for the init on top and the optimized on the bottom for the 12 runs. So in the nominal case, where you in red, you have the actuator behavior in both cases was well below 1. So it was well below the limit. So we had no problem with that. However, in the perturbed case, notice that the actuator behavior with saturation was more evident in the init case, in orange, was more evident in the init case than in the optimized case. And also the actuator behavior in the perturbed case in green, which didn't suffer saturation, was more frequent in the optimized case than in the init. And also one can note that the tube, which is in dashed black, the tubes is in the optimized case is constrained. However, in the init, because we don't constrain these tubes, are violating the limit, and actually violations occur more often in the init case. So in summary, we did an experimental validation on a drone with widely used controller, and we showcased the importance of the input sensitivity inside the constraints. The main limitations is that the trajectory optimization is still not in real time. It takes about average 6 minutes for a 7-second trajectory with 4 to 6 waypoints. And so far we focused on UAVs only, but these concepts are actually general. So we need to apply it to another, we need to consider another robots. So for this, that's motivated us to the final contribution at RAL that was accepted recently. So the motivation is that previous works focused on UAVs, while the sensitivity framework is suitable for any system. And we want to show the importance of our method in increasing the accuracy and the repeatability within repetitive tasks, such as package handling. And also we want to show that this method can be used with a standard manipulator having a standard controller without any additional hardware necessary. So for this, we consider a robotic model in the joint space with the Q dot, Q double dot being the joint angles, velocities, and accelerations. The robot has to manipulate a payload AL, which can be seen as an additional link of the robot at the end effector. And the parameters of the end effector can be adjusted as so. And so we consider actually the uncertain load parameters to be the mass, the center of mass of the payload, and also the inertia, which is a subset of the big inertia matrix, because the inertia matrix is symmetric. So we take less parameters. And modifying the last link of the parameters and applying Euler-Lagrange formulation, one can obtain the model explicitly in terms of the parameters of the load. And for the control task, actually, we let S being the position and orientation of the robot be the quantity of interest to be controlled. And then we applied this joint space torque controller based on feedback linearization. And we seek the best controller possible for these kind of tasks. And our focus was actually in the sensitivity is to increase the accuracy of position and linear velocity, which is denoted by X capital. For this, we actually calculate the task state sensitivity, which would be a Jacobian multiplied by the state sensitivity matrix. And then one can deduce the ellipsoid in the end effector state space, and then the kernel matrix can be deduced. And then we actually consider the new norm, which is sensitivity norm, which is the maximum value of the maximum eigenvalue of the new kernel matrix. And the optimization here is to optimize the shape of the trajectory, respecting the same constraints as before, but here we add also constraints on the joint angles and the joint velocities. And two scenarios would be considered. The first scenario A, which is sensitivity minimization at the final time. We seek higher accuracy at the final time, and this is with trajectory 1. And scenario B, sensitivity minimization at specific time of interest, T is equal to TW, and we seek increasing the end effector state accuracy while in motion. And this is with the trajectory 3. Trajectory 2 was omitted just for the sake of the time. The perturbations were done by randomly in the simulation by randomly sampling from the uniform distribution of the ellipsoid. And we took simulation runs of perturbed 30 simulation runs. And in a real experiment by altering the physical payload. As such, we have the nominal case and then we have 14 in the perturbed cases. And we did in total 15 experiments. The physical modifications actually included the payload mass of between 1.6 to 2.4 kilogram with the inertia variation up to 20% and deviation in the center of mass up to plus minus 3 centimeter on X and Y and 0.35 centimeter on Z. And this would affect all the parameters considered. So in simulation and without integral term inside the controller, which is based in scenario A, we aim only on minimizing at the final time the sensitivity. So for trajectory 1, the average target reach was about 1.2 centimeter, and it decreased to 8 centimeter for the optimized case with a much less variance. However, for the experiment, the results were more pronounced. In the experiment, you have on the top, you have the actual experiments, and on the bottom, you have the visualization again. It's worth noting also that the trajectory is way different in the init and the optimized case. And we got actually an improvement from 2.2 centimeter in the target reach to 1.1 centimeter with much less variance for our method. And comparing the uncertainty ellipsoid, it's evident that we reduced by about 50%. So now with integral action for trajectory 1, we add actually so that to see how the integral would increase the robustness of the methods, we consider two additional cases, init I and opt AI, with the integral action, and for trajectory 1, of course, and with the same scenario A. And we consider two scenarios, additional scenarios, that the robot stops at the final time, TF, and or we have allocated additional time budget of 5 seconds for the integrator to compensate for the error. In the init I, we improved from 2.2 centimeter to 1.7 centimeter in the average target reach in scenario A, and further to 1.5 centimeter in scenario B. However, for the optimized case, it was the improvement was from 1.1 centimeter to 7 millimeter of the average reach, and further improved to 6 millimeter. And it's worth noting that in the optimized case, without integral term, without post delay, it still outperforms the init I with integral and with post delay. And we did a simulation campaign of 10 distant trajectories for these cases, init I and OPT AI, which actually validates this experimental data. And for the scenario B, we actually are interested in minimizing while in motion the sensitivity at a point of interest, TW. We display for the sake of time the nominal case only, init I on the left and OPT AI on the right. So in simulation, for the position, based on 30 simulation runs, we got improvement of 28% in position and 29% for the velocity, while in the experiment, we improved for 17% on the position and 46% on the velocity based on 15 experiments. And here we display the actual trajectory of actuator of the fourth actuator, the actual actuator behavior of the fourth joint. Here the input tubes capture well, the input tubes in red capture well how they perturb the input behavior in green. However, there was instance where the tube violation occurred, and this was due to the first order sensitivity analysis, exclusion of some additional sensitivities like friction, and the inherent approximation of the package nominal parameters, which is really very difficult to measure. So in summary, we did an experimental validation on a manipulator within the task of package handling. The simulations and the experimental data showed effectiveness of our method, reaching up to 50% improvement. And we have a good performance for our method without needing really to add integral terms and post delays. The main limitations is that trajectory optimization is far from real time. It actually takes up to 60 minutes with 2-second trajectory of 4 to 6 waypoints. And there were instances where the perturbed behavior of the system violated the predicted tubes, especially for the inputs. So in conclusion, our main contribution was the validation of the sensitivity framework, tube-based trajectory planning with the sensitivity analysis. At IROS 2023, we explored this joint optimization of both the trajectory and the controller gains. At EQUAS 2024, we empirically validated the sensitivity framework for a standard drone with the commonly used controller, the PX4 controller, having real physical perturbation with the task of navigating through a window. And we extended this framework actually to include additional robot which is much more complex in scenarios of package handling, and we managed to improve we improve the accuracy by about 50%. In future perspective, despite several efforts, the trajectory optimization is still very slow. So we advise to explore neural ordinary differential equations, which actually depends on a neural network to estimate to solve the ordinary differential equation, and maybe you can have better timing with these kind of approaches. And also we advise to explore some software packages like Akados, which provides fast and embedded solvers, which are better than the ones that we are using. And also one can robustify any function of the states or inputs and optimize for power or time. This is really useful for time optimal trajectories, where you can just put the constraints on the states and the inputs and optimize for any other objective. And also one can add additional external forces or friction. Wind is possible. You actually, the wind, the torques that is by the wind actually depends on some nominal knowledge of the parameters like the mass, especially, for example, in dynamic positioning applications for ships. It would depend on the mass of the ship, the structure of the ship, and some nominal parameters. With a feedback with a feedback controller, you can take a nominal knowledge of these parameters and you can apply the sensitivity framework. So I want to thank you all for listening.
Thank you very much, Ali. So I give the hand to Fabio to start the question session.
Okay, thank you. So first of all, I would like to thank Paolo for inviting me here today. It's always a pleasure to be here. So thank you again. And also, I would like to thank you, Ali, for your PhD, for the manuscript. I really enjoyed to read it. It was really nice to read them. Very nice figure, very nice experiments. So congratulations for that. And okay, I have a few questions that I think I've already put this question in my report, but I will ask you also today. So I will follow the presentation. So if you go to slide 16.
16.
Now, just a question about the kernel matrix that
Yes.
you have here in this, and that you define at the bottom of the slide. So I think in the next slide you call it K pi, K theta.
Yes.
And so you need to compute the inverse of this matrix.
We actually
Do you have the guarantee that it's always invertible, this
we
matrix, or
actually
not?
never wanted to calculate the inverse, because if you look at the radius
Okay.
of the tube, it's just the radical of the k pi. So we didn't need actually to compute any inverse of this matrix.
And so you have this just in the definition of the ellipsoid, but you do not actually have to compute the inverse.
No,
Okay.
not at all.
Okay. Okay. So slide 18.
18. Yes.
So you say that this you consider a new cost function, but I think this cost function was also considered by the previous PhD student, the lambda max. And so what is really new with respect to the previous thesis?
Thank you for the question. Actually, so I started my PhD at the time where Pascal was at the middle of his PhD. So it was somehow like we were working on the same theory, more or less. So it was at that time we were actually validating this approach, and so maybe you would find it with Pascal's defense, but it was also me was also involved, and I was working on this stuff also. So it was a new for me and
At the
Pascal.
time, okay. And another question is that you didn't mention in the presentation, but is in the manuscript. Then to write this optimization problem, you pass through a discretization. So you use some Bézier curves to do this. And so why this choice? Could you have used other approximation? This has been done previously, but why this choice?
We didn't really focus. Thanks. We didn't really focus on the trajectory representation that much, because at the end of the day, you are converting from the infinite dimensional space to a specific representation. So we didn't really explore whether using another kind of parameterization would have a better effect. And to be honest, working with Bézier curve is somehow intuitive, and it was not the main contribution of this thesis, actually, the Bézier curve. It was with Pascal. Okay. So I kind of continued because I didn't face any problems with it. And some modifications happened on the way, just about how the functions are written. But more or less, I kept the representation as it is.
Okay. Also, I have a question about this optimization problem. So you didn't really characterize this problem in the manuscript. So as I can see, the first constraint is a linear constraint, so with respect to the unknown, the vector A. But is the cost function nonlinear with respect to A? The other constraints are also inequality constraints are also is a nonlinear, a general nonlinear programming problem. What class of optimization problem is
Yeah,
this?
it is in general a nonlinear program. You mean the class, now you want to say about the E optimality, I think?
Yeah, it was more about the type of optimization problem. It's not, I mean, for example, is the cost function convex? Is
non-convex, of course, yeah, with the same
kind of characterization.
Of course, yeah, with the it's because the dynamics are nonlinear, and also the tube would depend on the states in a nonlinear fashion, so everything is nonlinear. So yeah, of course, it's not convex and.
Okay, so you cannot
No.
say much more. Okay. And another question was in the slide 22. When you have the input allocation matrix. So it was a question about you have a k, the parameter kf multiply all the matrix. Yeah, because I mean, there are other formulations which is not really the case. So I was wondering.
No, it is actually, you're right. It's a kf multiplied by all the parameters inside.
All the parameters.
And here kt, maybe you would say you would follow up. Maybe kt is not k tau, or maybe it's not the Dirac coefficient, but it's a kf multiplied by kt.
Okay, so this multiply everything. Yeah, maybe it's a different definition of the parameters that I had in mind.
Because you asked, I think, about kt. What is the SI unit of kt?
Yeah.
Just following on this, in this scenario here, kt would not have a unit because it's multiplied by kf, so kf would be having the unit.
Okay.
KT.
And so it's a different definition. Okay. I understand. Also, I have a question on it was slide 28. Was about these violin plots. Okay, I see what is on the vertical axis. What is it? Was it in the on the horizontal axis? And so the width of this plot, what does it represent?
And the horizontal axis is just the
I mean the size of these violin plots. What is it? I don't see the unit.
You mean the size of
the width of these colored bars?
It tells you where is the most of your samples concentrated around the work. So if you see, for example, if it's fat, then it means that most of your samples are concentrated at this region in particular.
Okay, so you don't have
flat,
you don't have a unit of measurement on the horizontal axis. I mean, it's not.
No, there is not.
Okay,
it's just that the cases on the horizontal axis.
Okay. So then a general question. You mentioned this in the conclusion of each part of your presentation about the computational cost that is still, I mean, still a bit too long. We are not in real time. And so you mentioned that with respect to previous work, before was 30-40 minutes, now is about a few minutes. And so first of all, what did you improve? And the second question is it possible to finally go to real time? What should be done to do this?
Okay. So the question is really big. I will chop it into parts and I will answer. First of all, about the computational times, for example, I will talk about the drone and then I will talk about the manipulator. In the drone case, yes, it's indeed, before coming to this PhD, it was about 20 minutes with Pascal. But then we did some improvement on how we actually write the functions and so on. We cleaned the code and we managed actually to decrease a lot the computations by 10 times. But this was not this was done while using the not correct tools, let's say. So we didn't use, for example, Casadi or automatic differentiation, which would make the thing much faster. So we were not using the correct symbolic tools, and still we had this 2 to 4 minutes. I would assume that if we if this was the priority of the thesis, we could have done many approaches like switching to Casadi, I don't know, like decreasing, let's say, the time horizon. And there is a lot of actually a lot of stuff that you can do, that you can have something instead of minutes in seconds. But I don't know if you can do it online in our approaches. But there is a student who done it online, and I will speak about it if you are interested in tube MPC. So I will be speaking about it right after. For the actual Manipulator part, I think we have done a really good job because other people in the team, so I will display what other people did. So Andrea Pupa, he's one of the collaborators in the project, and his idea was actually to optimize depending on some the parameters. For example, the mass of the end effector is somehow not known or something. So you want to design the trajectory in the null space as to mitigate the effect of uncertainties in the parameters of the end effector. And he formulated this as the common trajectory optimization problem as we do, and he included the tubes inside the inputs and so on. However, for his approach, it took him 48 hours. So it's more or less the same as we did. I was not aware of his work until recently. It was same as we did, but we were like just 1 hour. So it depends really with this kind of tools. It depends how you implement it and how you do it, and so it's complicated thing. So I think he can advance more in the computational time, and we can also advance more. But it's about really like finding the right tools, the right packages, and so on. I forgot the next part of your.
No, I think you answered the question. It was
But
very
I
good.
can speak if you are interested in MPC. I can maybe Andrea will speak about
later. Okay. Then I have another small question. It was in the experiment that you did with the quadrotors.
Yes.
And so in the thesis, you wrote that the goal was to pass through a window. And so I was thinking a rectangular standard window. So why did you consider a circular one? Is there a real reason for that?
Because I read this paper. This paper here.
Okay. The guys from
Circular Gates.
University of Zurich. Okay.
But it's not my. I don't. It's not that I like round shapes or something.
But this simplifies somehow your formulation, or there is no a special
not really,
reason?
because we didn't actually consider any tubes, let's say, on the states of the system. We could have considered tubes on the states and minimized any other objective function, but we didn't do that. Maybe, yes, if you consider tubes on the states, maybe it's better to have a circle than a rectangle, but we didn't do that.
Okay. And also I have a question on the experiment with the quadrotors. You consider different configuration, different object, etc. So the question: how did you measure the nominal parameters in this case, PC in this case?
So basically, PC would be the center of mass, would be the KF, K tau, and so on. So KF and K tau is easy. You just find it online. You find it from any research paper with the same propeller. It was not complicated. You speak about PC, right?
About the nominal parameters you considered 11 different cases. The mass, the center of mass, I think is changing.
I consider actually.
How do you measure the actual center of mass in the nominal center of mass?
Yes, you're right. So the mass is easy. You just put a balance. The KF also, you know the propeller, you can deduce it from any manufacturer. But for the GX and GY and GZ, for the drone engineers, they know that with the 2 fingers you can just put and slide, and you can know for sure where is it coincident with the geometric center or not. Okay. But so basically, when we manufacture this drone, we take into consideration that the center of gravity would be in the geometric center of the drone, so it wouldn't deviate that much.
So you didn't use a CAD model or somehow 3D model of the drone to estimate?
It would be really good if I did that, but no.
Yeah, okay.
We did it the old-fashioned way.
Okay. And I don't know if you have more time. Can I go on? Okay, let's go. I have another question about the actual final application. This was more about the manipulator part. So when I read this part, I thought about robots that are used in warehouses. For example, I was thinking it's kind of Amazon robot that is manipulating packages. And in that kind of application, you don't know anything about the boxes. You don't know the mass, you don't know the inertia. So what can you do? Is your method is still usable? What kind of assumption should we do?
I think if you know just the maximum deviation, like in the W matrix, you can just know what is the maximum deviation that you can suffer. You can really apply it, because we don't really need to know the parameter. Where is it located in the ellipsoid? It can be anywhere. So you can, even if you have, for example, a bottle of water, let's say, that is half empty and the inertia is varying. If it's within the ranges, then why not? Yeah, you can. It's applicable.
Okay, and also in this part, it was slide 47. I think that was the slide before. And so here you mentioned that I think it was the previous one in which we see the trajectory. Yeah. So you mentioned that you, in terms of precision, you have a gain of 2 centimeters accuracy for this trajectory.
For in the experiment, yes, but in the simulation it was 1.2 to 8 millimeters.
Okay, but I mean the disadvantages, as far as I understood, is the trajectory could be quite could be longer, could be, I mean, and so okay, you have 1 centimeter something better in terms of precision of accuracy, but you have much longer trajectory. So where is the trade-off, let's say?
Yeah, it is true that the trajectory actually is way different. It's not that trivial to get from that to that. But I would say that if you look at, for example, when you say about maybe you have concerns about the power consumption or something, the actuation seems really the same. You know, like we are using the same actuation, maybe higher speeds because it's longer, and you need to reach at the same time, with the same time. Maybe higher speed, but more or less the actuation didn't differ that much. So in terms of actuation or power, we didn't lose much, but we gained in accuracy. So I would say that maybe the only limitation is that you have to wait 60 minutes, I would say. But then for this kind of repetitive task, you just calculate it one time.
Once,
and why you need to calculate every time? So
okay. I have 2 more questions. So one question is about, and so also in this part with the manipulator, you considered the same cost function as for the quadrotor, the minimization of the snap. And so in terms for the quadrotor, in the quadrotor, let's say literature, this is quite common. I mean, there are a lot of work that consider this kind of cost, but is for a manipulator really a good cost function? Is really pertinent in that case?
yeah, you're right. So we wanted to actually just compare with any trajectory. We didn't really care about this trajectory to be really designed in some way. So maybe some applications would need this trajectory to be designed in terms of power, let's say. We can minimize power, we can minimize velocity, something like that. But why not to minimize the snap? So it's why not. I would say the main concern that we had is that we want a trajectory to respect the limits and to be as smooth as possible. Whether it was the minimum snap or whether we use another objective, I don't find that.
Yeah, okay. Is that a reasonable choice? Anyway, yeah. Last question is about was slide 52. Is still related to the computation time. So you said here that the computation time is 60 minutes, considering 4 to 6 waypoints. And so my question is, what is the effect of the number of the waypoints on the computation times? Why 6 waypoint and not 60? Can you elaborate a little bit on this?
Yeah, of course. Thanks for the question. This is up to 60 minutes. So basically, if you consider 60 minutes, it's with the 6 waypoints. And in this implementation of trajectory 1 and in trajectory 3, I considered 6 waypoints. In trajectory 1, I think 5 waypoints. Yes, of course, if you increase the number of waypoints, you are increasing the decision variables. yeah, of course, you would need more time. But I think if I want to comment about this, the trajectory optimization, I don't think that I can go less than 4 waypoints, because already with the 4 waypoints, you are getting 3 degrees of redundancy for each of the states, let's say, for each x, y, z. So for each one. So already this number, let's say, is somehow reasonable for this kind of trajectories. Of course, if you are going for longer trajectories, you would require more waypoints, but it was for 2 seconds. So how much you need as a waypoint?
Okay, 2
and
seconds,
each part of these waypoints is a Bezier curve of its own of 5th order. So
that's enough for 2 second trajectory. Okay, I'm done. Thank you very much.
thank you.
Thank you, Fabio. Okay, so I will now change role because I was also a reviewer. So I will let myself speak and and so now take the role of reviewer. So thank you to Paolo, Marco, and Antonio, of course, for trusting me in reviewing your thesis. So I would start with a few comments on the thesis. First of all, congratulations for your RAL paper, because I think it was not accepted when you sent the document, and now it is. So that's great. I really praise the work, because I think it was, I mean, I understood that you based your work on the state sensitivity framework, which Paolo started in 18. So this is also a bit tricky, because you take over on work which is quite mature, and you have to add things in. So it's not an easy exercise. Sometimes it's better to have a fresh problem. And plus it requires some theoretical understanding. I know that your supervisors have all very high standards, so that's also makes the pressure increase on you. And it seems you kept up with the with the pressure, which is really good. So at first, when I read it, was not so clear for me what was the contributions, but today I think you showed them very well in the slides. And I mean, what really you added to the existing framework developed in the last 6 years. And of course, the theory was also accompanied by a lot of experiments with drones, and also even with the Panda. So I think that's also acknowledgeable, because of course it's experimental robotics, so time consuming and energy consuming, sometimes even more than the equations part. And plus, also, even in the drones, I appreciate the fact that you're dealing with different models, because I'm not at all, I'm very naive in drones. I don't know anything, but then as one reads your manuscript, you will see that sometimes you're using Antonelli's model, and sometimes it's another model. So I think you have to also understand all these dynamic models. So even in the field of drones, you are not just doing one drone. And basically, I think also one thing which is also appreciable is that it's not very long. So this is good for a reviewer viewpoint. You have a short text, but dense and clear and well written. And in fact, it turns out that today I have not so many questions, which on one hand embarrasses me, but on the other, I think it means that you really are clear even today. So yeah, I think it's a good thing in the end. Okay, so this was about the thesis. Now about the questions. So yeah, at first when I received the manuscript, I was a bit surprised, because Paolo asked me to revise your manuscript on planning, and at least in the title there is planning, and I'm not at all an expert in planning. So at first I was plus drones. So really a bit out of my knowledge. I was a bit scared to review this, but then as I read it, of course, it seemed like very interesting and applicable to to robotics in a broad sense, but I still have this thing in my mind, which I also evoked to Paolo, because Paolo presented this in Nantes, and something which for me is still strange, but it's in the paradigm, so it's very high level question, is that at the end of the day, you never speak about sensors. So it seems like your your method is kind of open loop, and even when you start framing it, you start with the state equation, which we all know, but there is not the measurement equation. There is x dot equal f of x, but there is not y equal. And then at the end of the day, one wonders why, I mean, certainly it's great to solve this problem, but in principle, when we do robotics, we have sensors, so we can use the sensors. And there is no mention at all of a feedback loop in your work. So I understand that, of course, a thesis in France lasts 3 years, so you cannot do everything in 3 years, but at least elaborate. Plus, also, you're in a group which historically always did sensor-based feedback, so why not use the sensors? Or how would you use the sensors if you had another thesis or if you had more time?
Well, in the framework, we didn't actually model the sensors or anything about the sensors. We actually assumed every time that we have a perfect measurement of from the model. Like we didn't really add some models to, let's say, estimate, or we didn't design maybe some observers, let's say, or we didn't really tackle these kind of problems. So for the sensors, we use the sensors on the drone, for example. We use the IMU, we use all the sensors there to actually do the feedback loop. For example, let's say...
Can you show, like, for example, you're on 32,
like here,
maybe?
for
Yeah.
example, you have
Yes,
the
exactly.
RD is... so we, of course, for the let's say, for the drone, you have this kind of markers that actually we take from the Vicon system. The experiments were done in this room in particular. We have this Vicon system that actually gives the position of the drone, but then actually what you have inside the drone, I don't know if I can zoom or something, we have IMU, we have all these kind of sensors that we depend on also with some extended Kalman filter, EKF2, so to actually measure the states. But inside the framework, let's say in the framework sensitivity, we didn't really deal with the sensors, and we didn't deal with having like noisy measurements and so on. We always assumed that the measurement that we are getting is the right measurement, and we have no, let's say, uncertainty in it.
But yeah, but you're not using them.
Using
the IMU and
it's we are using the position.
I mean,
we are using the for the angles.
Yeah, maybe the 132. No,
this one.
Yes, maybe not this one. You mean? Yeah, this is.
Yeah, but you need the angles of the quaternion, for example. You need the quads. So this is so you have a quaternion set point, and you have you basically need the rotation and so on. So it's all of course.
Okay.
You have
so
to
you're not
use
using exteroceptive sensing, or are you? You're just using proprioception. No?
Can you define exteroceptive? I forgot.
I mean, you're not. Can you trust those to track your trajectory? Those are directly giving you the trajectory that you want to follow.
Which ones exactly you mean?
Like, for example, the IMU or the sensors that you mentioned before.
You have like some sensor fusion with multiple IMUs, so you can select. I think with the PX4 controller, you have maybe 4 IMUs that you can actually really have a good estimation of the quaternion, or a good estimation of the states of the system. If this is what you mean.
I mean, I would tend to say that if your goal was to track a trajectory, it's a Cartesian trajectory, for example, with parameter uncertainty. If you have reliable exteroceptive sensing, you can do it just with the sensing, without the model. Even if your model is uncertain,
Yeah,
you
but
don't need all this. This is what I mean. So I think one of your underlying hypotheses is that you're not really, for example, you can use a camera or even the
But-
LiDAR or GPS or the mockup.
Yeah.
Of course, the mockup is a bit cheating because I assume that when you will
it's,
deploy your drones, there is no mockup. But nevertheless, I think these sensors, but maybe I'm mistaken, are more proprioceptive sensors. No, they're telling you the state of the system, which is useful, but it's very liable to error. That's where the parameter uncertainty is tricky. It's like odometry. But if you had exteroceptive sensing, then you would be relieved from parametric uncertainty. But again, maybe I'm wrong, so please prove me wrong.
Yeah, I am not sure outside the lab settings in the UAV how it would be the case outside the lab or outside the mockup or something. I don't know if I understood you correctly, but I don't know. Probably I didn't understand the question. That's why.
For example, the window.
Yeah.
If you saw the window, you would just do some visual control to go inside the window.
Okay, I understand.
How? Suppose tomorrow I give you a camera and I tell you can see the window. How can you plug the camera in this scheme? Can you update your trajectory or some? Probably it's.
So depending on the position.
You never wondered about it, but imagine you had the opportunity
So
to measure the window in real time instead
this is
of.
like visual servoing.
Yes,
now.
for example.
What they do is. I have no experience in that, but I would answer that you can actually locate the center of the window by the figure, and you can depend on some visual servoing scheme of the position, and you can implement it. I have no idea, but you can implement it as a control law also. You have the position and so on, but I am not an expert. I'm not an expert.
Okay, so because in your first when you start with the differential equation C dot at the beginning of your slides, I think.
Yeah. This.
I think really at the beginning, well, of your problem when you say that the state equation, and then you have a controller. So that's why when I started reading the thesis, I thought, oh, great, so he has a feedback loop. But somehow your feedback loop is not updated in real time. It seems like you turn on the drone and then the drone follows the trajectory.
No.
It's in real time, but with those feedback loops that you show
Of
with
course,
the
of
IMU
course.
and so on.
Yeah, the feedback loop.
Okay. Yes.
real
Okay.
time,
Okay. So I think it's.
We give the trajectory as a feed-forward trajectory. Like we give it a trajectory, but the drone, of course, it's operating by its own. We just
yes.
You give the trajectory actually by this. I don't know if I understood you correctly.
Yes.
But you give RD, which is the position, velocity, and acceleration. You have RD, R dot D, and R double dot D. So you give it, and the drone have this control loop inside it that works and does all of this.
Thanks a lot. Yes, I think it's a misunderstanding because I was thinking exteroceptive, but here, yeah, I understand. And then the drone is autonomous, and yes, but with those so the data is from those sensors. Okay. It's the same with the manipulator. You could have a force sensor. Yeah.
You mean the desired is just you are sending the trajectory to the drone. You are sending via Wi-Fi or something. You're just sending a CSV file, let's say, with the common set points that you want, and the drone is just closing the loop and following this trajectory.
Okay. And then the computational time is also an issue because you cannot change the trajectory once you've calculated it offline.
Yes, of course. You cannot really change the trajectory. You just calculate it and you apply it for the drone.
Okay, and then when the feedback loop is closed online, it can be a bit far from the trajectory.
It can
and
deviate, yes, of course.
Okay.
It can deviate. Yeah.
Okay, perfect. Yes, I didn't. Yeah, at this point, it's true that it was not clear for me, but now it is. And similarly, there is a bit of a lack. Well, Fabio pointed at it a bit, but I think you don't speak at all about implementation and the non-linear optimization. At some stage, you mentioned Casadi, but it's a bit late. It's in the chapter on the panda, so it looks like, and I understood also from how you answered to Fabio that Casadi is only used, you discovered it towards the end. So how did you do all the rest? Because these are, so there are so many non-linear solvers out there. Which one are you using? What is the problem? I mean, this part is a bit lacking.
It's just about Casadi. I will start with Casadi. Yeah, of course, we used it just for the manipulator, because if we didn't use it for the manipulator with the older tools, we had to wait like days to just generate the model with all the ODEs and the sensitivity and so on. So with Casadi, in 1 second, we were able to generate the model with the parameters. So what the problem that took days in the older tools, in Casadi, it took 1 day. So, 1 second, sorry, 1 second. So yeah, so that's for the switch of for Casadi. I believe that if we have switched also earlier to Casadi in the drone case, it would have been really a boost, let's say. I wouldn't assume anything else. It would be a boost in the computation, but I don't know how much. For the second part of your...
No, before Casadi, how were you solving this? Which, I
okay,
mean, even,
was using
are you aware of the underlying math, or were you using like black box solvers?
No, the symbolic toolbox is SimEngine. It's based on the eigen
Library.
yes, it's symbolic. So basically, it was at the time, it was really good and so on, but with the advancement, you know, Casadi has been, I think, 5 years now. It's not been a long time. It's, yeah, with the advancement and so on, I think Casadi is a way to really advance, let's say, in the time of the drones. But even you use Casadi with the manipulator, it's still really problematic, because the manipulator is a more complex system. Example, if you want to just print, let's say, the inertia matrix of the manipulator, it would be like 40 pages long. So it's not something that is easy to calculate. So that's why the forward integration, let's say, for the manipulator, it takes about 50 seconds just to compute one forward pass along the trajectory of 2 seconds with the sensitivity, with the computation and everything. It takes about 15 seconds to just do this pass.
But okay, but again, I mean, maybe it's a naive question, because I didn't, I never touched these tools. But these tools, I mean, I know that there are many ways of finding an optimum of a nonlinear cost function. Like you can use
you mean solvers
particle
now?
filter, genetic algorithm,
okay.
what you mentioned, neural. So since I think one thing that was a bit lacking was, since you don't write, as Fabio also stressed, you're not writing the cost function, it's a bit difficult for us to understand, the kind of problem you're solving and how. And related to this, but this is maybe the next question, is that sometimes when you use nonlinear programming, the little I know about it is that with regards to a convex problem, of course, is that your time changes a lot. Randomly from, I mean, randomly no, but it can vary from one iteration to the other. Yeah. So this is very dangerous, because you don't, maybe once it takes 1 millisecond, but the next iteration it takes 100 milliseconds to find a solution. So these aspects are not detailed. Then of course you cannot write everything in the thesis, but maybe you can explain a bit now.
Yes, the computational times actually also would depend. One thing maybe you missed, that it will depend also on the initial guess. Let's say when you start and how you will finish. So also it depends on how long is the horizon that you have, how many seconds, and how much you sample it, how the frequency that you sample. You can take a frequency of 100 hertz or 50 hertz. It differs significantly. And for the computational times, I think that you want to know the solver that I am using. It's a constraint optimization by linear approximation. It is somehow a black box. It's not a gradient based approach. And this approach is actually converting the nonlinear problem into a linear program at each iteration and modifying this trust region so that it can calculate it. So it's somehow a black box, and actually this is... I am not sure it solves a QP. I don't think it solves a linear program, but I don't know what is it and how it does it. It's been since a long time. Okay, so I don't know if I answered the question.
Yeah, okay. And on slide 43, I think. I was also, this part also in the thesis, it was not very clear with the notation. I couldn't understand. You are putting a Jacobian here. So is this actually the robot Jacobian or not? Are you, so, can you explain this?
Yes, of course.
The end effector.
So the variations of the end effector actually in the position and velocity would, so you want to calculate the variations of this with respect to the parameters. And to do this, you would have the variations of this with respect to the states, Q and Q dot, multiplied by the variations of the states with respect to the parameters. The variations of the state with respect to the parameters is something that we know, state sensitivity matrix. We put it aside. That is a Jacobian, which is Jacobian capital X. So I call it just Jacobian capital X, which is equal to the partial the derivation of the capital X, the position and the velocity of the end effector, with respect to the joint angles and velocities.
Okay, so you map the sensitivity with regards to joint towards sensitivity with regards to Cartesian operational space.
Yeah, exactly. You have three.
Okay, and this was also done on the drones, of course, but it was not called J. Because on the drones also you have from thrusters to pose.
No, but it directly in the drones, when you were calculating the pi, it was directly that you can have del f over del q, so it was...
it was already in the right state space. Okay.
But here, like for example, if you take RE and VE, they are not explicitly represented in terms of the parameters. So you know, so RE and VE does not really depend on the parameters directly.
RE and VE, yes.
Yeah, so there is no relation.
Yes,
so
yes, yes, yes. Yes, I understand. Yeah. Okay, thanks a lot. And maybe last page, on the last slide, maybe, page 53?
53.
Yeah, slide 53.
53.
You mentioned now this is... no, what did I write? Well, when you spoke about the drawbacks, I couldn't understand this at the end. Yes, 52. Main limitation. I didn't understand the second drawback, instance where the behavior of the system.
Yeah, I am answering this. Sorry, you want to continue? But I understood your question.
Yes, can you explain?
Yes, so basically, because in the tubes of the inputs, this is here we are estimating the maximum deviation of the inputs that we can suffer along, for example, T4 with the input tubes being in red and the perturbed being in green. So we actually try to deviate, let's say, the box package inside this parameter ellipsoid. But however, there are some cases that this actually you had a violation. I don't know if you can see it. There is some sort of violation of the tube. So this violation actually happened, and we have to acknowledge it. And we think that it's because maybe of the first order sensitivity analysis or some exclusion of this additional forces that can affect the robot, like friction or... So that's why we added this. But however, in the state, I don't know if I managed. So I just want to show you another result. Yeah. So for the state, here we projected the tubes on the end effector position X with the init and the OPTA for trajectory 1. The tubes seemed really good. For example, for the X position. But when you go for the Y, it violated a little bit, When you go for the Z, it was good. So there was some instant where the estimated tube from the simulation was not perfect on the experimental data. That's what I mean by this.
Okay, but then that's a lot of work.
Yeah, you have
do
to
that.
consider
You need
all
to-
the uncertainties, and so it was yeah.
Okay, I don't know.
But there is a way to mitigate this with Amr, for example. He's another collaborator. What he did is that he considered that there is an external force acting on the drone, for example. He ran some experimental runs, and he could estimate this residual, let's say, force that's acting on the drone, and he was able to mitigate this effect from the control action. So he was able to estimate these kind of forces and eliminate its effect in the controller. So his tubes were really nice and were centered as he wished. So it could be possible that you can also do this kind of stuff.
Okay, thanks a lot, Ali. So now I will transform again into president, and I will let Isabel, who is examiner, ask some questions.
Okay, so do you hear me?
Yes.
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 So thank you very much. So first of all, I would like to thank Paolo for inviting me in the jury, and I would like to apologize not to attend to the defense physically today due to timetable constraints. So I would prefer to be with you, but sorry for that. I also would like to join my colleagues and to congratulate you for the presentation, which follows quite with the faithfulness, the manuscript, and with additional simulation and also videos. So you had a lot of questions, so I had similar question to Andrea and Fabio, but I will try to have new ones. And so first of all, I would like to come back to the implementation that when you implement the optimization process. Yes, I had maybe more comment because Andrea was already asking you how did you implement. I mean, I have the comment maybe that you didn't describe in your manuscript how you develop your symbolic library that you with all the calculation, and that could may be useful that you explain how you develop that, because I couldn't understand why, for example, in slide 29, you said that it took 25 minutes to compute trajectory. I don't know, yeah. 29, yes. You said that maybe at the beginning it took 25 minutes to
Yes.
compute trajectory, and after that you have only 2 and 4 minutes. So it's not so easy to understand why you have such is it because you had more waypoints on your trajectory? So what was the reason?
No. Yeah, thank you for the question. No, it was not related to actually how you what is the trajectory shape and so on. It was more related about how we defined, let's say, the model, how we defined the controller and so on. It was related more about let's say changing the functions itself, how the computations were done. It was not related to, let's say, how the optimization works in the sense that we change the trajectory and so on. So we kept the same representation of the trajectory. We kept everything the same. Even the controller is the same. but we changed just how everything is written and how everything is structured. But yeah, I agree that maybe it would have been better that I have put all my codes online so that everybody can benefit and so you can see what was done exactly. I regret that not having this done already. Yeah, but for the tools I was using mainly for the symbolic representation, I was using SimEngine. It's as I told Andrea, it was based on the engine library, the one from C++. And for the optimization, I was using, I think I documented this in the manuscript, I was using this toolbox from Python. It's a nonlinear optimization toolbox. And I was using the Cobila solver that solve it without the need of using the gradients, because the gradients were very costly at that time. I don't know if I answered your question.
Yes. Thank you very much for the answer. I mean, I understand maybe that could be helpful, even it's not, you won't put the code in your manuscript, but maybe you can open it on in open source, but maybe in appendix, you could maybe just explain more which the library that you were using, and that could be helpful for future students, future researchers that will follow your work. But thank you for the answer. Yes, I had also a question regarding to a question of Andrea about the planification of the trajectory. Since you do with waypoints, and since you are in a case where you use a mockup system, the trajectory that you define, it is in some kind of an inertial frame, and I mean, yeah, it's related to the question of Andrea, and if you wanted to, I mean, you use different kind of frames to follow the trajectory if you have your onboard sensor?
I am not sure if I understood the question, but
Yeah,
I
because
will just
when you plan your trajectory, so you just program some waypoints, and waypoints in the waypoints, is it, how do you define them?
Okay, yeah, now I understand the question. So basically, I don't just plan waypoints. I plan the full trajectory at each time step, and
Yeah.
I give it to the drone by Wi-Fi, and the drone will have a Jetson or a computer on board that would take this let's say at each time step would take the position, velocity, and acceleration. Would give it to the controller. And the controller would follow this at each time step.
Yeah, I agree. It's not only waypoints, since it's all the trajectory by using this Bezier curve or polynomial. I mean, yeah, but that's in which frame do you follow that, your trajectory?
In the frame of the Metivier room, in the frame that is actually, so we have the Vicon frame.
Yeah. Okay.
Vicon,
Okay.
it's located in the center of the room, so
Okay.
it's located in the center on the ground. So it's the frame that we use to.
Yeah, but if you would like to use in another frame, it could be also possible to do.
I would say yes. Why not? It would be possible, yes, of course. You just have to do rotation from one frame to another.
Okay. Yes, I would like maybe that you come back to slide 27. It was the table with percentages, where, yes, I mean, yeah, there are the KF and KTO, which are the thrust and drag coefficient. Is it right?
Yes.
Yeah, so that's normal that the percentage on the z-axis is very big for kf, but I don't know why there is 0 for kt, because I mean it is the drag coefficient. So I know in your equation that you didn't follow exactly the paper, because there is a multiplication between kf and k2, but why there is no effect on the k2? I was surprised.
Yeah, I would say maybe Keto would affect more, let's say, if you are doing some maneuvers in the heading of the drone, like you're changing the heading more. But in our implementations in this, we were not really changing the heading much. So it was not really dynamic excited, the yaw angle, let's say. But yeah, so didn't have that impact on the states from the. I don't really know exactly. I expected actually to have like a very small number, but it was compared to the other parameters, it was really negligible.
Okay.
So, and this was done for a statistical study of many trajectories, so it's not just for one trajectory. So this is for all the trajectories, which and irrespective of the controller choice. So it's also for all the controllers.
Okay.
So it showed this performance.
So also I appreciate a lot that you did some comparison by using different controller, geometric controllers, like hovering controller and sliding mode control. Yeah, you didn't have time maybe to come back to that during your presentation, but it's written in the manuscript. Yeah, I was wondering if, I mean, the difference were not very big between all these controllers. So what is your conclusion? I mean, we can use different controller with such robust trajectory planning, or do we have to also use more robust controller like SMC, or what is your conclusion again about that?
I would say that it depends for the controller to be tracking quite well. It depends on the tuning of the controller. It's a very essential element for any controller to track. So in this, the tuning for the controllers. So basically, even a near hovering controller or PID can be tuned in a certain way to be more robust than other controllers, if you want. But it's all about the tuning gains. So what we did actually in this to give a fair comparison between the controllers and to really see the control the how each controller would behave and to be able to compare them across the cases. We in the init case we tuned the controller gains for the near hovering, the lead controller, and the sliding mode, so that they have this the same, more or less the same deviation for the init. So maybe we degraded the sliding mode controllers, maybe we improved, for example, the near hover. So we did all of this so that we have the same tube, let's say tube size at the final init. And this was done for many trajectories, it's not just one. We tuned these controllers in this way, and then we say, okay, from this is the criteria. Okay, they are reaching the same median. We want from there to optimize. And the optimization showed that actually sliding mode, for example, is subject to, is really influenced by the controller gains. Variations the controller gains can really affect it. So I would say that at the end of the day, these controllers would really be a function of these gains that that improve the tracking. So yeah, for the sliding mode controller, it was more affected with the gains, but less affected by the trajectory optimization if the gains are not tuned correctly. But if the gains were tuned and also the trajectory, it achieved a really good performance.
Okay.
So this is about like, of course, you can implement a robust controller, but if it's not tuned correctly or tuned very well, it will not behave quite well.
Yeah. So another comment and question about the work, the philosophy of the work. So I know that even you explained well in the state of the art that robust control method is a different philosophy with respect to robust planning, what you did. But I mean, I still have the feeling that it could be interesting to compare also the work with you mentioned in the state of the art, for example, the MPC with some adaptive estimation of some on certain parameters, because what we have seen is that the proposition is quite as high computation. So I know that you have also some perspective to decrease the consumption, but would it be interesting to compare with approach like MPC, which is very well known? So what do you think about that?
Okay, thank you for the question, Isabel. Yes, I will be speaking about what Tommaso did then, about the tube sensitivity-aware tube model predictive control. So you know that MPC is an open loop, so you have really no information about the control behavior, and MPC can give you good performance if you know the model very well. But if the parameters are not known, then you possibly have a degraded performance for the MPC. So here, Tommaso, what he did is he introduced this sensitivity-aware tube model predictive control, and he wanted to minimize an objective function. It could be anything, could be like, for example, the accuracy or something, with including the tubes inside the constraint, like the tubes on the inputs, so that he adds some additional layer, let's say, of robustness to the MPC, especially in the cases where you need the drone to follow, let's say, a really challenging trajectories. So, but the computation of the sensitivity was a little bit not trivial, because you have this function, which is the feedback gains of the MPC controller, which is the input sensitivity, actually, the del U over del P. When you want to differentiate, when you want to use the chain rule, you will get del U over del X. And this del U over del X will tell you how the future inputs would vary with the future, how the future states actually are affecting the future inputs. So this was not really trivial to get it, because the actual input of the actual inputs of the MPC is from the not explicitly defined as function of the parameters. It's an output of the optimization problem. So it's the solution of the optimization problem. So then Tommaso, what he did is actually he estimated, he used QP as the MPC to be a QP, and he had this solution, which is W star, would be the X star and U star, and then he did this Jacobian of differentiating the solution with respect to the initial state, the current state, sorry, and then you get these matrices. And from these matrices, you can relate how actually future states would depend on the current state, and how future input would depend on the current state also. But this is not what we wanted, actually. We want to know how the future input is varying as you vary the future states. So with a lot of math involved, and he actually applied for a TRO paper, we actually managed to get these feedback gains, which allowed us to compute the input sensitivity and put it inside the MPC formulation. And I think he used the multi-shooting prescription maybe for the MPC and the SQP, so around this current solution. So if this answers your question, yes, it was done somehow with MPC, with Tommaso, a PhD student at the time, but now is a postdoc here.
Okay. So thank you for all this additional information. So that it's very interesting to mix also this MPC. But about the time consumption, I don't know, but maybe there about the programming, they need to. You need to.
Yeah,
to,
I agree.
to
Yeah,
compute.
continue. Sorry.
No, but just to compute with maybe some library toolbox like Kazali or some or Kados you were mentioning also, because it seems to be a lot of math, a lot of programming.
Yes, I agree. Actually, Tommaso made it online because he decreased, let's say, the horizon. It's I think as I read, it was about 0.5 second with the 50 hertz, and yeah. So basically, and he was using Akasadi, our automatic differentiation tools. So he was able to run it online. It's possible, and his work with the simulation plus he did the experiments recently, and the thing is working quite well. So it is possible that when you change the tools, you can have possibly online, and if you set the problem correctly, if you set the dimension of the problem and limit yourself, you can do it online.
Okay. Okay, maybe my last question would be on the perspective. I mean, you mentioned the neural ODE
Yes.
to decrease the time consumption. So can you say more about that?
Yes, I can definitely say we have also another collaborator. It's called Simon Wasila. He's Atlas. His goal was actually to just learn the tube sizes, the tube on the input and the tube on the states. And for this, he proposes the gated neural network to provide accurate estimation of the tubes. However, of course, you can do neural networks, but then you are limited by many limitations, which are, for example, that it's valid for a specific range. So you cannot really, you have to retrain your model. He took 10,000 randomly generated Kino splines to train his model, and he got really good accuracies, very good accuracies. And he applied for RAL, and it was really nice work. But at the end of the day, you have to always retrain the model whenever you change the ranges, whenever you change the controller, gains, whatever. So, and also still he was not able to do it online, sorry. So the computations were still online. So I think with these kind of problems, it's really difficult and really tricky to do it online anymore. But with the right tools, as Tommaso did, I think you can manage. And for the neural ODE, I saw many papers speaking, mentioning neural ODE as an alternative for faster computation. But I am not sure also that if I go for a neural ODE that I will get real time. Because, for example, Simon was using something that depends on learning, and he significantly improved, let's say, the computational times, but still he was not able to run it online.
Okay, thank you for the answer. And as a final comment, I would like also to mention that I had the honor to follow all the work about the sensitivity that Paolo was building a long time ago. I mean, I was in the jury of Quentin Delma, then Pascal Bro as a reviewer, and Nicolas de Cary. So I am very happy to see today, Ali, that you could also manage to test experimentally all this theory, and you show also that there are several perspective and direction on that. So I congratulate you for that. Thank you.
Thank you.
Thank you, Isabelle. So now that the external examiners have all spoken, I give the floor to Antonio Franchi, who was co-supervising the thesis. Ciao, Antonio. Nice to see you. And he's professor at University of Twente, and he can also now speak.
Yeah.
about the thesis.
Thank you, Andrea. And my apology for not being there. I would have been very nice to be there also live, but unfortunately it was not possible. Thanks, Ali, for the nice presentation, and also thanks for all the work you have done together with all your colleagues. It was really a pleasure to do my little bit in the supervision of your PhD. So I'm not going to ask any question for the sake of time. I think there were so many interesting topics being discussed already. So I will leave the floor to the others, maybe also to Paolo if he wants to comment on some particular aspects related to the control law, for example. But yeah, this is mainly what I want to say. So congratulations for what you have done so far. Let's see what will happen after the meeting we will have. I hope I can congratulate with you also for the achievement about the PhD. It's still unknown, of course, still uncertain. It's not granted, but so far, I mean, I'm very happy with what you have done.
Thank you.
So, Andrea, I leave the floor again to you.
Thanks a lot, Antonio. Yes, thank you very much. So yeah, hopefully he will get the PhD today. And I let then now Marco Cognetti speak also. He's chair de professeur junior at LAS, and he was also co-supervisor.
Hello, everyone. So first of all, I would like to thank Ali in general for working with me and accepted me like as co-supervisor during the run, because I actually joined the co-supervision of Ali like in the half of his journey. So thanks for that. I want to also thank Paolo and Antonio for accepting me in the co-supervision team of Ali. I also thank all the committee. Thanks, I mean, for accepting to review the manuscript and for all the interesting questions that you may have. So I have just, I mean, a couple of maybe clarification that I may give also to the committee for describing a bit better, I mean, what Ali did. So the first one was about the question about how you know the parameters like in real experiments that actually Fabio was asking in the first place. So one of the advantage of the sensitivity framework is actually that one, so that you just need basically an estimation about the nominal parameters of that are certain, and in the case in which you want to compute the tubes, a maximum range about that. But during basically the experimental part, you don't need the exact value of the parameters, because in practice you cannot know that, and that is the practical advantage in using the stuff. So that was one of the challenge of Ali also in presenting the results, because obviously you cannot have some sort of measurement, for example, of how much you are close to the boundaries of your stuff, but obviously that is the advantage. So this is the practical usage of the sensitivity framework. Then, I mean, I also may have a clarification for Andrea, so that I have one reply for everyone. Is about the sensor usage, about the sensitivity. And in this case, there is a bit of clarification about what we do offline and what we can do online in this case. So first of all, the sensitivity framework works in closed loop. So obviously, I mean, let's say that the controller, so and basically the system that you are controlling is the closed loop one and not the open loop one. And that is basically one of the main differences. So we are not doing everything in open loop. What you are doing in open loop in the case of Ali is the playback of the trajectory. So once basically you have find the trajectory is most insensible, yeah, in that case we are going, let's say, in open loop. But just because we are doing a trajectory optimization in that case. For example, in case of the work of Tommaso that is working in MPC, this is going onward, let's say, the online fashion for factor, let's say. So it was just for a bit of, maybe, I mean, Paolo can describe it better, but I guess it's the whole point about the sensitivity stuff. That's, I mean, maybe, I mean, I will leave the floor also to Paolo that maybe you add some more details about this.
Thank you, Marco. So, Paolo?
Thanks. Thank you, Andrea. So yeah, I will. So I will talk about. I mean, Ali, your journey at the end. I start first by thanking the jury, especially the reviewers who did a very thorough report with a lot of comments that were well funded and helped us also in the discussion that we had after we received the reports and in preparing the presentation. Helped us to let's say be more critical, understand also better what we did, what we couldn't explain well, what we could have explained better, and so forth. And also thanks for being here. So yeah, and thanks to Marco to have already started some clarifications that I wanted to make. I just want to add another. If you can go to the slide with perturbations on the drone, which I think it is where Fabio had the question, and he also had a question, if I remember well, on this point on the report. So as Marco said, the main point is that we never have to know the value of the parameters in the perturbed case. We only need to know the value of the parameters when in the nominal case. The nominal case is when nothing is attached to the drone. This is the only thing that we need to know. And we need to know the range of variation. But then when we attach something, that's it. We don't need to do anything because but we have the assumption that the parameters will change and will stay inside the range that we imagine. So this is the assumption, but we never need to do an identification when we attach something or we perturb the parameters. You see? So PC is only for the nominal case, which is the one without anything attached. And for the manipulator, it will be PC will be the value of the parameters in the case in which in the box, I don't know, there is a nominal mass point. Then we add stuff that we don't have to do anything at all. So this is one point that maybe didn't come across well, but we think it is a good point of the method because it doesn't require. Then for the control, I think that there is a little bit of misunderstanding because of course there is a control. There is nothing is open loop. So the quadrotor is controlled, the manipulator is controlled. And one point is that all these computations are done by taking into account also what specific control will be used on the drone or on the quadrotor. If the control is changed, the optimized trajectory will be different because it will be optimized for another kind of controller. So every controller will have its own optimized trajectory. So here there is an exerotepsis sensor, of course, which is Vicon, because otherwise you cannot fly. So there is a feedback on the position, the error with R. So R comes from Vicon, because then V also comes from Vicon because it is the derivative of R, and the rest comes from the arm. So for the question of why, I don't know, if you have vision, then and use on board vision to control, I don't know, you want to pass through the window or whatever, then you wouldn't need this because it will be robust. I don't agree. Why? Because it is the same as in Vicon. Also in this case we have Vicon. Vicon is very precise. But when we have uncertainties in the parameters and actuation constraints, if you start changing the parameters with respect to nominal value, you will have deviations in the trajectory, even if you are having feedback from Vicon, because you are imagining that your mass is 1 kilo, but your mass is 2 kilos. So you have feedback, but the feedback will mitigate but will not exactly. So you will have a deviation. And if the deviation is too large, maybe you will saturate, you will incur in saturations. While when we do this planning, we guarantee in advance that if the variation is inside the range, we will not saturate never, let's say, I mean, in the first order analysis. Yeah.
For the Vicon or the INU,
Yeah.
you do not consider that the measurement are uncertain.
No, we don't consider. No. There is no noise. So in this framework, we are not. I mean, we have ideas on how to. So it's something that we have some ideas on how to. It is something that has to be done in the sense of just seeing how to do it, but it's not. Yes, so there is feedback, but the feedback is assumed to be noise free. So, but there is feedback, of course. The controller is there, and the planning knows that there is a controller, and that controller will have this strength, this weakness, and so forth. Okay, this just to clarify these points. Now, coming to Ali. So Ali, I have to congratulate you on two things. I mean, at least two things. So one is that I felt you gave really a good presentation. I think that you repeated it more times after our last repetition, because I think it's been improved compared to when we did it last time. And so congratulations on the presentation. Also on the supporting slides, on the media, I think you did a good job really in presenting. So this is my opinion, of course, and the jury will speak for themselves. And also during the PhD, I think one of your main strengths have been to really the willingness, the lack of fear, I will say, in testing experimentally all this machinery. Because you sometimes, when, especially when maybe, I don't know, you are more into methodological theoretical advancement, then you have some kind of fear, feel of testing too much because you don't know, never know what could happen. But you had really this attitude of, I want to see what happens in real cases, and it's managed to set up and run very nice experiments with all these masses attached to the drone, which were an added value. And in fact, this showed up also, I would say, in the award that you got for the EQUAS paper, because there, the reviewers recognized that there was really a real experimental validation, besides the fact that the theory was nice and the method was nice. So you've also been one of the first in the group to do a thorough and good experimental validation of all this theory that we were developing until you, mainly on the theoretical simulation part. So this is a big achievement also for the group, I'd say. So thanks for your work, and I wish all the best for the rest of the career, and and then also maybe for the next. So when we see each other in half an hour.
Thank you very much.
Yes, perfect transition, because we will see each other in half an hour. We will have a meeting for deciding. And so are there any questions just before we end, maybe, from the people, or comments? Okay, no questions. So then, yes, we invite you please to leave the room, and we will call you in roughly, yes, I think half an hour.
Thank you.
Thank you very much.
And then maybe for Antonio and Isabel, so I think I will, because now we go to another room, so I will generate a Zoom link, and will send you by email the Zoom link so you can join on the Zoom for the discussion, okay? Okay.
Okay,
See you later.
see you.
So we discussed in the other room and for a bit with also Isabel as examiner. And so as Antonio said, now we have the verdict and it's positive. So I will shortly read you a draft of the rapport de soutenance, which summarizes the advice of the panel on your defense today. So then, of course, there will be the official one in a few days. So this is a draft. During his PhD defense of high quality, Ali Srour presented his work, which was fully in line with the manuscript. The presentation was very pedagogic and rigorous, well-structured, and effectively illustrated by videos. It allowed the panel to appreciate the technical and scientific mastery of the issues addressed. So Ali managed to position his work on state sensitivity framework in a relevant way and illustrated his contribution to the field. So he in particular applied theoretically and especially experimental skills. And in fact, we particularly appreciated the experimental part, which included many test campaigns carried out on 2 different types of robots, UAVs and serial manipulators. And this really proves the generality of the framework, which had been mostly proved theoretically on simulation before. So given this, we very strongly encourage you to release and share the code, which was developed during the thesis. This is something that we, the 3 of us, I think, mentioned either on the rapport or today, Isabel. So we encourage you to release this code for the entire research community. This is about the presentation. Then concerning the questions, you faced a long question and answer session, which also satisfied the panel members. And during this exchange, you showed your expertise on the subject by answering all the questions. And you even anticipated some questions because you have some hidden slides which provided additional material. And you were also very honest in acknowledging the help of your collaborators who helped you or worked with you on some of the topics. So given all the above, I'm very glad with the other members of the panel to award Ali Srour the doctoral degree in automatique, productique and robotique of the Université de Rennes. Congratulations. So maybe also you can read the sermon if you wish. This is optional, or you can say a word, whatever you wish.
This is optional?
I think, yeah, it's up to you if you want to read it or not.
Oh. Ok, en français. En présence de mes pairs, parvenus à l'issue mon doctorat en planification robuste pour systèmes robotiques, et ayant ainsi pratiqué dans ma quête de savoir l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexibilité éthique et dans le respect des principes de l'intégrité scientifique. Je m'engage, pour ce qui dépendra de moi, dans la suite de ma carrière professionnelle, quel qu'en soit le secteur et le domaine d'activité, à m'en tenir en conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. Merci. Just for the acknowledgement, I just want to thank. I didn't prepare anything, so it's just on the go. I want to thank you, Andrea and Fabio, for this review process. I was really inspired by the comments, so that I prepared the slides. It was really nice to see another point of view. I really thank you so much, and also for being present at my jury. I want also to thank Isabel for trying her best, but she couldn't manage, but for the questions and everything. For Paolo, it's 3 years. I don't know what to say, but I thank you very much for accepting me in this PhD. I learned a lot, and you were really nice to me. And yeah, I want to say that we had really good collaboration together. And the idea that you actually pushed me pushed me really hard to attain these contributions. So without you, I wouldn't be in this place today. So I want to thank you. And also I want to thank Antonio for first for his criticism. Always he used to criticize, but the criticism was actually really an important part of my PhD, so that I advance and I really take things and I really change it. And also for the motivation, because with the criticism, he was also motivating me every time, sending me emails, motivation, and so on. I really appreciate everything that you have done through this PhD. Although we couldn't really meet that much, but just having you in this PhD was really a pleasure. Thank you very much. For Marco, I don't know what to say. Thank you for accepting me to be one of my supervisors during my second year. And I think one of the projects that we really were together was the final one at the RAL, where we really worked together, and especially at night. So sometimes in the middle of the night, we were exchanging messages on Mattermost. We were debugging, doing, and so on. So it was really like you cannot really find everywhere someone who would do that. So I am really lucky, I would say. So thank you very much. I want to thank everybody who's attending my PhD, whether it was on YouTube or whether it was presential. I really appreciate it. I want to especially thank the permanents. I really enjoyed our meetings, our, let's say, discussions. And I think this team is one of the best teams that you can possibly imagine, because you have a good spirit, people are eager to learn and so on. There is a lot of people who have high experience, very high experience, I would say. And I will not name them because they are already known everywhere. So I don't know. Yeah, and I want to thank my Lebanese friends who came actually from, they stopped their work, their everything to come just see me. I want to thank also my girlfriend, Marie, for coming. And I want to thank my family for supporting me and being here for me. And I want to thank someone who's not able to come. Is my father. My father actually died while I was in the second year of my PhD. Maybe many of you do not know that, from liver cancer. So my father always looked at people in a different way, the people of science in a different way. He used to admire people who really have higher ranks in the science or as researchers. So his own wish was actually for me to become a PhD holder, and now his wish, I would say, it came true. And I want to thank him for always pushing me to pursue knowledge. And thank you all for being present. Thanks.
Picture of together if there is a volunteer for taking